This is PUMACY Technologies presenting Value 3S use case number 4 called Human-Robot Interaction in Semi-Automatic Assembly Processes. PUMACY Technologies is a leading provider of knowledge and data analytics solutions founded in 2000 as a spin-off of the Technical University of Berlin and the Fraunhofer Institute in Berlin, IPK. Our main customers are leading manufacturers in the aerospace, automotive, pharmaceutical, and machinery industries. PUMACY's smart service solutions cover the technical, methodical, and organizational aspects of data analytics solutions. We have strong expertise in data aggregation, data mining, process mining, as well as in the application of semantic technologies. For this purpose, we bring in both technical expertise and prototypes of software tools for context-oriented services, big data analytics, and decision support. The high-level objective within values is defined as to design, implement, and evaluate state-of-the-art methods and tools that reduce the time and cost needed to verify and validate automated systems with respect to safety and security requirements. Use case 4 is about the application of verification and validation methods in a collaborative robotics assembly scenario where a human assembles an electronic transformer unit consisting of multiple parts. Obviously, safety and security is very important within human-robot collaboration and an interesting and still relatively new field for the development of verification and validation approaches.
As we can see in the simulation, the transformer coils are transported on a roller conveyor carried by the small load carrier. Once the load carrier reaches to a specific location sensed by the proximity sensor, robot picks the first transformer coil with the help of a gripper and places it on a workstation at a safe distance in front of a human worker. This step repeats until all the transformer coils are unloaded on a workstation by the robot. After placing all the coils on the table, robot then automatically moves to the rear side of the assembly process, where it picks up the E and I metal sheets from the pallet and places them on two conveyor belts on either side of the robot. After unloading the sheets, the conveyor belt moves until a new sheet package is detected by the proximity sensors. This sequence is designed in such a way that each sheet is separated approximately by 5 cm distance. In this way, the metal sheet can be picked up easily by the human worker, which means that this assembly is much more convenient and an optimal ergonomic and temporal evaluation can be achieved.
As seen in the simulation, the automation of human-robot collaboration tasks cover many requirements that needs to be evaluated by test cases targeting safety and security. The need for this use case is to design and develop a digital twin model that help us to investigate possible faults and errors which can occur during the assembly process. Simulation data can be generated and used for validation and verification before testing in the real environment. Accordingly, accidents can be avoided in reality by using data analytics for failure detection and diagnosis. As a result, it will save time and effort in overall system design, development, setup, and testing. The main method used in use case 4 is called failure detection and diagnosis, which is a process monitoring method for testing and minimizing downtimes and to increase the safety of operations in order to reduce manufacturing costs. Several tools will be involved in the use case, namely Feral from Fraunhofer Institute for the failure injection, Cyros Studio from Festo Didactic for simulation and digital twin model development, and machine learning for model-based detection and prediction of failures as part of a data analytics pipeline and tool. Our main expectations are to be able to use data from multiple sources for the verification validation process, for example, data from robot itself, data from a variable fiber optical sensor system for activity recognition, and data coming from localization systems like proximity sensors and ultra-wideband system. Secondly, we expect to build and train a machine learning model that can diagnose and predict potential failures based on heterogeneous data sources.